I'm Paul Casabon. I'm the head of public sector at a quantum computing company called Alice & Bob. And the company's headquarters is actually in Paris, France. I work for a little US subsidiary based out of Cambridge, Massachusetts. And our team, there's about 6 of us scattered across the United States right now. We're going to be growing to 9 staff members this year. I'm based in Westchester, New York, and my colleagues, some of them are up in Cambridge, so it's really easy for us to get to Connecticut. And my talk today is, it'll take a village to make quantum computing useful. I got to meet a few of the audience members here, and here's exactly the audience I had in mind for this talk. And so, because, Quantum CT is building that village. Great consortium of government organizations, academic organizations, and for-profit organizations. In my job at Alice & Bob, I focus on building technical partnerships to build all the technology around what my company focuses on, which is just the design of the quantum processing unit, that little teeny tiny piece at the heart of a quantum computer. And the company's plan is to just stay there, just be the designer of that chip, and then even from who's going to fabricate the chip at scale, someone else, and everything, all the other technology, someone else is going to build it. We need to co-design with them today. So my job is to form our own consortium for a for-profit company, similar to the consortium, the regional consortium that you guys are doing a great job building in Quantum CT. And personally, I would like to have Alice & Bob on this list soon. So a little bit more about the company. We design a qubit with built-in error protection. We were founded in 2020. The crux, the intellectual crux of the company's technology actually was born in 2013 through academic collaboration between Yale and ENS in France. You may have heard of another company locally of Quantum Circuits, Inc. Right? That's the commercialization of that Genesis idea in 2013 in the US, and Alice & Bob was from that same Genesis, but in France. So we founded the company in 2020. We've raised over $150 million in funding, and we just have a small company, a little bit over 150 people. In my role as the head of public sector, I've had the pleasure of forming partnerships with DARPA, and ARPA-E, NVIDIA, Google Cloud, and some of the vendors that we need to build a minimal viable product of a quantum computer, Quantum Machines for controls design, they're out of Israel, and Blue Force for the refrigeration system to get our superconducting qubits cold enough to work. They have a US presence as well in upstate New York and Brooklyn, but they're based out of Finland. I'm proud to say that we just had a ribbon cutting ceremony in a facility outside the perimeter of the northeast perimeter of Paris, where we built our own nanofab and cryostat farm, 40,000 square foot state-of-the-art facility. We've invested about 50 million euros into this facility, and this is going to allow us to do internal iterative design of our chips. Some of the genesis, again, the core ideas of the company's technology. I have some QR codes here for the papers. We first demonstrated what's called a cat state. You may have heard of the Schrödinger cat thought experiment, which asks, what's going on with quantum mechanics at the teeny tiny level when I connect its implications to the macro scale, everyday level. Is the cat dead or alive? As asking, does quantum mechanics make any sense at the macro scale? The photon states on our qubits involve lots and lots and lots of photons, so many that it's practically macroscopic scale. So the field calls these states macroscopic hat states as a play on that idea. In 2023, I had a demonstration of being able to have a bit flip of multiple seconds. And then a few years later, we'll jump to 2025, really, to squeeze cat to get to over 30 minutes, where we can have take over 30 minutes on average for our qubits to have a bit flip error get introduced. From other quantum computing companies, instead of 30 minutes on average, they're talking about numbers of microseconds. So the crux of this company's technology is that we only have to correct for one type of quantum error, whereas other companies have to correct for two types. And so we've taken a 2D problem down to 1D, and there are lots of interesting implications of that. The first implication is that we need fewer physical qubits, tangible qubits, to work in conjunction with each other and classical computers to form error-tolerant, effective, or logical qubits. For us, we anticipate, our papers say we need about 20 physical qubits for one error-tolerant logical qubit. Other companies with similar technology like IBM or Google, they'll need thousands to create one. That's one of the reasons I joined the company, was the tech was very compelling to me. And I'm a physicist by trade. So my talk today, that's just a little intro of the company, but my real talk is why is quantum computing worth developing? Why has it been hard to develop? And the types of collaborations that exist now, will exist soon, and that are still missing, even on the future horizon. Also, please feel free to ask questions. So just raise your hand at any time. So why is quantum computing worth developing? For me, the promise of quantum computing is that we'll be able to answer scientific questions and do design of physical systems, iterative design on quantum computers that are not, it's just not feasible to do even with today's supercomputers. So when you look at new architectural buildings or new cars or new airplanes, those things are designed iteratively with computer-aided design systems. Right? What if we had computer-aided design systems for chemistry, for material science? We don't have those today because the classical supercomputers aren't sufficient enough to compute these systems quickly enough to do iterative design, computer automated design. But for me, this is like the main thing that quantum computing is most useful for. It will be a design tool for catalysts, drugs, battery materials, and so on. And this little schematic is an idea of how a quantum computer would have to work in conjunction with a high-performance computing or supercomputer together to form these sorts of design systems, iterative computer-aided design systems. You'll have some sort of some optimization loop on the left and another sub-loop on the right that's focusing the thing that is the quantum computers are especially good at, just focusing the quantum computer on just that sub-piece of the overall compute flow. In this case, it's looking at quantum chemistry, hybrid with the classical high-performance computing workflow, from molecular configurations to ground state energies and reaction modeling. So here in the yellow is just using a quantum computer to calculate what's the ground state energy of this molecule. And it's doing the rest of the modeling on a classical HPC. When I talk to potential partners of people who already run today's supercomputers, mostly I talk to public sector organizations. So I'm talking to the Department of Energy's national laboratories. I went around and I asked them, when you look at the potential use cases for a quantum computer in conjunction with HPC, how does this map with what you're currently doing on your HPC systems today? So these numbers are coming from some of the labs I spoke to, from NERSC out in Berkeley, California. Los Alamos National Lab is the middle pie chart out of Los Alamos, New Mexico, and the InSight program. So these are their answers of what are our end user scientists using these incredible machines for already? And you see from NERSC out of Lawrence Berkeley National Lab, 13 to 38% of their current supercomputing use falls into what can be accelerated by quantum computers. For Los Alamos, there's two flavors of national labs. There's the open science labs, which is where NERSC is operating. Then there are the labs that focus on national security. Okay, we can't actually ignite nuclear bombs, so let's use simulation of our supercomputers to test what would happen if we did. That's like Los Alamos National Lab. So that's why the percent is actually significantly higher for Los Alamos than it is for NERSC. So these folks are already if we could accelerate 40 to like 55% of their compute workload, that'd be a tremendous acceleration of their science. So, okay, that's the first topic. Any questions? Yeah.
Maybe just some context for those coming in late. Like, Alice and Bob is the name.
I'm not Bob. yeah. Alice and Bob is the name of the company. And when the founders decided what should we name this company based on this research, they said design principle is there should not be a Q in the name. And when you're a physicist doing like an intro class on quantum information theory in colleges like here, you might say Alice wants to send an entangled photon to Bob, who wants to send one to Charlie, and so on and so on. So it's a physics joke. Just going through the alphabet of names. And our mascot is the Schrodinger cat because of the cat qubits that we built. Thanks. Yes?
So in the pie charts, those applications are, so how real are they in terms of the practical? Are they really practical in this?
Yeah. So these pie charts are what are these national lab compute facilities doing today? Right, so they're having scientists write detailed 50-plus page proposals for why they should get this precious resource of compute time, dedicated scheduled time, to do their science on these machines. So these are what's happening already.
Wait, is it just more about the research phase, or are there real applications from those?
Oh yeah, sure. So these sorts of facilities, they were doing simulations of the COVID vaccine and the virus. They're doing nuclear testing simulations. These are all things that are very practical to very basic science and everything in between. So yes, some of them are very basic science research with no immediate application. And some of them are, like the nuclear testings in lieu of blowing things up. Very practical. Yeah. But it's a spectrum.
Hi. So this is like way over my head. I'm a neuroscientist by training.
Yeah.
We're at the back of the train. Way up. What is a qubit?
Oh, yeah. Sure. Thank you.
Like way.
Oh, thanks. Thank you very much. So, yeah. So, non-quantum computers, so-called classical computers, because they use classical physics. So classical computers, they have what are called bits. And a bit is just something that has two states to it that you can easily go back and forth between and easily copy from one to the other. So you might have a coin and this controller, and say when the coin is heads up, this controller is face up, and when it's tails up, this is like this, so I can easily copy information between them. And the physics of these physical things that are instantiating information or bits, the thing that I'm doing to them is obeying classical physics, flipping it. I can describe that flip with just classical physics, no quantum physics required to explain the flipping. Quantum computers will say, what if the thing that I'm manipulating to represent information, the thing I do to manipulate it to store information, what if I need quantum physics to describe the physical manipulation to change its state? That is called a quantum bit, or qubit for short. And there are all sorts of very unusual implications of what if the physical thing I'm using to store info is described by quantum physics. Lots of very weird stuff that go into why certain types of mathematics can be done much more quickly with these sorts of qubits. And there are many ways to build qubits. And Alice and Bob built one type of qubit. Here in another room, I think there's a room filled with other quantum tech companies. And they build qubits out of very different physical objects. But if you look at the math describing the physics of manipulating those objects, if you kind of squint and you just look at the math is the same between all of them. It's quantum. Does that make sense? Sure. Okay. I'd love to come back and do what is the technical side of things here, but I wanted to just say a little about that. Okay, so that's the first topic and a little explanation there. The next topic I wanted to touch on is like, why is it hard to develop? Besides quantum mechanics being hard to understand. But if you look at the field, the village, people who are building these things, right now, for the most part, different subsystems that go into building these quantum computers require extreme specialities. People with very specific skills with a PhD in this versus a PhD in that. They're both physicists, but this physicist studied something radically different from this one. They can barely talk to each other. So, how do you represent the problem as a quantum circuit? Quantum circuit is like a drawing of the logical manipulations, those manipulations. Flip it. Don't flip it. Flip it if this happens. And there are ways to draw that symbolically. That's what's called a quantum circuit. How do you compile that circuit, take that algorithm, and make it into beeps and boops on the quantum computer? How do you protect the quantum computer from noise from the environment? Just like a little too hot, little thermal fluctuations, vibrations, things like that. Through error correction. Error correction requires some non-quantum computer that's constantly measuring what's happening on the quantum computer, deciphering what that means, and then changing something on the quantum computer to correct the error. So every quantum computer is going to require classical computers to do a continuous loop. Even keep it a zero requires continuous error correction. How do you lay it out on a device? Through lithography, physically. What does the chip look like? And then, which device should I pick? This is especially useful, important to think about today because of all those different companies building radically different types of machines. Some of them have different strengths. Yeah.
The one I'm interested in is packaging. How do you package something like this? I/O seems like a major bottleneck.
Yeah, absolutely. So that's one of the topics I wanted to touch on. I'm going to talk about 5 different partnerships. Yeah. So you have all these different considerations, and what typically gets done today to make a demonstration, like some sort of research paper comes out of a group. How do they do it? Well, first they pick, say, they focus on material science or say chemistry. They'll say, all right, first let's fix the chemistry problem, define the chemistry problem. Okay, tweak the compiler to make sure that it is especially optimized for this problem. All right, now let's choose a special error correction layer. Now let's choose, and then the hardware team gets the bill. This is sort of the cat on the bottom is getting the bill from the rest of the team flowing down. So the application is compiled to the hardware stack and the software stack. Usually the stack is not designed to the application, usually. I'll talk about some cases where it can be right here. So there's some recent work by a group out of the University of Wisconsin-Madison of a QR code to their paper, where they said, actually, let's try to design all of these different layers holistically and see what we can do. And in their paper, they were able to say, for a particular chemistry problem, they were estimates before the research was done, estimates that it would take a quantum computer about 22 years to calculate a particular property of CO2. And when they said, let's holistically design the whole hardware software stack just for this problem, they got it down to a single day. And I point out this group because we put an application together to the Genesis mission from the Department of Energy to further this work at Alison Bob and University of Wisconsin-Madison and Argonne National Lab. Okay, so to your question, types of collaboration now, soon, and this is the third and final topic of the talk. And the QR code there points to a paper by a researcher, a luminary in the field named John Preskill. And he wrote a paper. That paper is a very useful lens to what is my job, personally. So I'm looking for technical partners to go from error mitigation, which is correcting for errors after the fact, after the computing is all done, to active error detection and correction while it's being done. Other type of partnership is going from rudimentary error correction to scalable fault tolerance. Another from early heuristics. We think this is faster on a quantum computer because we'll run some experiments to point to it, but we can't really prove it with math. To mature, verifiable, the algorithms definitely go faster based on mathematical theory. From exploratory simulators of what would happen on a quantum computer using a supercomputer to model the quantum computer, to credible advantage in quantum simulation of, by simulation here I mean like simulating chemistry on a real quantum computer. And then the last one to your question is replacing scientific high-performance compute abstractions for today's quantum computers, which are typically called noisy intermediate scale quantum computers, where there is no fault tolerance yet, to extending these abstractions for fault tolerant quantum computers, which is what my company focuses on. So I'll go through these different sorts of partnerships really quickly. So from error mitigation to active error detection and correction, this is just showing how long on average it takes for one of our qubits to accidentally have a bit flip error. In 2020, it's like 10 to the minus 3 seconds. In 2025, we could start measuring it in many, many minutes. That's over 2,600 seconds, many minutes, 30 minutes or so. So we do our own internal design fabrication, but there's a lot of different sorts of science that's going on under the hood to make this work better. Most of the time our researchers take the materials for granted and take the nanofabrication capabilities for granted. Given the machine that can to do lithography, these materials, what can we do with that? So I'm forming research partnerships with academics and national labs that don't take those pieces for granted. They say, what if we use different materials? What if we tweaked these materials? What if we tweaked the machine that lays them down? What can we do? And there's usually a trade-off between academia or national labs versus companies. Companies care more about quality control, and the public sector has lower quality but more flexibility to experiment with things. So this is sort of like materials with nanofabrication co-design with the design of the qubits itself. So this is one major area of partnership. And one more here is once you settle that design space with those partners, then you say, now we're ready to produce things at scale. Okay, well now you need a different type of partner, a fab or a foundry, who's able to build things at scale, control their quality, control their costs. I've talked to lots of foundries in the United States. They're not ready for this type of device. They're not ready for these types of materials, these types of topologies or connectivities, these types of materials in the way that they're laid out. The foundries I've talked to in the US, I've said, it's going to take a year for us to get ready to start doing basic demonstrations of your technology here in the US. This is why I thought it was pretty interesting news last week where the US government and IBM put $1 billion each into a quantum chip foundry to be built somewhere in Albany with like a spin-off company of IBM. Because the foundries aren't ready for it right now. This will be the first foundry that will try to specialize in it. Okay, so just those sorts of partners. The next category of partners is going from rudimentary error correction to scalable fault tolerance. We have to build and operate machines with practical applications. And so here we're playing around with different ways to cluster physical qubits together and work in conjunction with these classical computers to do error correction. We've come up with a few ways ourselves. Google and IBM, they've championed a way of doing it called the surface code. We've figured out a way to do it with relying on extreme quality of the qubits and the physical aspects of the qubits for one type of error, bit flips, so we could focus this sort of overhead correction on just one type. So our problems are 1D, whereas other companies it's 2D, two types of errors versus one type of error. But we're working with academic researchers on what type of error correction codes that we use and what types of devices do we have to plug into the quantum computer to do the right type of measurements and to have them done at the right speed. Right now, NVIDIA, whenever the quantum computing part of NVIDIA is giving a talk, they'll have a logo slideshow of practically every quantum computing company on the slide. The main thing that they're trying to do their partnerships with is, given the hardware, given the mathematics of the error correction idea, here NVIDIA is saying, here is our GPU that will sit next to your quantum computer and decipher what these errors mean you have to send back to the quantum computer to fix it. Well, what's the speed at which a classical GPU can do this loop versus the speed of the quantum computer's calculations? For us, it's a huge mismatch. Ours are way too fast, and NVIDIA's are way too slow. We're trying to work that out. So NVIDIA is a nicer partner for this with other types of physical ways to build qubits that have slower compute cycles that are about the same speed as their GPUs. So there are other vendors who are building different types of hardware to do this sort of decoding on the classical compute side. And it's about speed matching. Let's get that. So then there's also going from early heuristics to mature verifiable algorithms. And like I said earlier, we're trying to go from NISQ to fault tolerant. And there's only a handful of fault-tolerant algorithms that have been verified mathematically to have different types of computational speed up. When they say exponential versus super polynomial versus quadratic in that computational speed up column, what they're talking about is you have a particular problem, and I'm going to make that, as I make that problem bigger and bigger, say I'm searching. Well, if you're searching through a bigger and bigger database, as that database gets bigger, how long does it take for your search algorithm to return the results? And you got the size of the problem getting bigger and how long it takes. Then you draw the curve and you say, is that curve quadratic, exponential, linear, things like that. So we want exponential. That's the best scaling, the fastest scaling. So the research partnerships that I'm building with national labs are applications that use these fundamental building blocks. You know, names like quantum phase estimation algorithm, time evolution algorithm. These are very, very basic pieces of a tool belt to build a bigger compute workflow, like calculating the thermal properties of a molecule. These are the sub-pieces inside of that. Then from exploratory simulators to credible advantage in quantum simulation. Now, taking those basic tools on the tool belt, going a little layer of abstraction higher to the applications, different research groups have done different estimates of what's it going to take for the hardware to solve this type of problem. On the top is material science or condensed matter. There's sub-problem examples. How many logical qubits is it going to take to compute something in a reasonable amount of time? And how many logical operations is it going to take? And if you take the number of logical operations, say the top one is 10 to the 6 to 10 to the 8, if you just take the reciprocal of that, bring it down to the denominator, that'll tell you the error rates that you need for your logical qubits to do a computation like that. So you need the error rates for the top one at 10 to the 6 operations. Your logical qubits will need to have an error rate of 10 to the minus 6, or 6 zeros before you get another digit in the error rate there. So the Genesis mission from the Department of Energy put out a request for information a couple of weeks ago. It's due June 8th. And they said, what's it going to take for the US to get a quantum computer that has 150 to 250 logical qubits with an error rate of 10 to the 8 in order to do these different applications. And they're focusing on material science and quantum chemistry